everyone. In this video, we're going to talk about sequences in series. And the first important point here is to distinguish what we mean by a sequence versus a series. Because in my experience teaching Calculus 2, and even when I took Calculus 2 years ago, I found that these two words were often confused. So first of all, let's just write an example of a sequence. A sequence is a list of items written out in a particular order. So you might have a sequence like 1, 3, 5, 7, 9, ... This is called an arithmetic sequence. And this is actually an arithmetic sequence because the way we got from one term to the next, the little pattern here, is we kept adding 2 each time. Another type of sequence might look like this. So we've got 1, 2, 4, 8, 16, 32, etc. And again, we've got a list of numbers separated by commas. They're written in a certain order. And here the pattern is that I multiplied by 2 each time. So I'm going to put multiplication by 2. I multiplied by 2. So those are good examples of sequences. And those are lists of items written out in a particular order. We're separating the items by commas. So I'm just going to make a note of that. This is a list. And we're separating things with commas. Comma is the little virgula if you speak other languages. Anyways, series on the other hand are quite different. So a series is a sum. So we might have a series that looks like, 1 plus 3 plus 5 plus 7 plus 9 plus ... So this pattern goes on forever. And if you ever tried to add that up, well, first of all, you'd be here for a long time because you've got an infinite list of numbers to add up. But you'd quickly notice that this sum is getting bigger and bigger. The more I add to it, it's exploding on me. And in fact, you'll never actually get a real number answer. If you keep adding bigger and bigger numbers, you'll get, something that approaches infinity. So this sum doesn't really have an answer. And this is what we mean by a series diverges. The sum approaches infinity. I don't get a real number like, 10 or something like that. It's not a very satisfying problem. And so this is a series. Series have the addition signs in them. Let's look at one more example. So another example of a series might be something that starts off like this. You've got 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... So I'm still adding up an infinite number of things. I mean, I'm going to continue this process till time never stops. But what's really shocking is if I could continue for, infinite time, and unfortunately my life isn't infinitely long to do this, but if I could, we would actually get an answer for this one. So here I'm adding up an infinite number of items, but this actually has a value. We get an answer, a satisfying answer of 1. I'm not going to dive into the theory of series right now. I'm going to do that in a different video. But what I want to emphasize right now from the start is that sequences are separated by commas. So that Q sound, sequences, almost sounds like a comma in the middle of it. And series is something with the sum or a plus sign. Okay, so that distinction is very important. Series means take a sum, and sequences means you've got a list of items separated by commas. Okay, so let's take a look at some important properties of sequences. This is not an exhaustive list, but will give you a feel for getting started working with this topic. So let's take a look at example 1. And example 1 is going to be written in the following notation. A sub n equals 1/2 all raised to the nth power. All right, so I want to look at this sequence. First of all, I want to write the terms. So we'll do that. And then I want to draw a graph. And then I want to talk about whether the sequence converges or not. Okay, so let's first of all write the terms in the sequence. So when n equals 1, I'm going to make a little table here, n and a sub n. So when n equals 1, I'm going to plug in 1 for my formula, and I get 1/2 to the first power, so I just get 1/2. And when n equals 2, I'm going to plug in a 2, so I've got 1/2 squared, I'm getting 1/4. And when it's 3, I'm going to get 1/8 and so forth. So if I were to write out the terms in my sequence, I have 1/2, 1/4, 1/8, 1/16. I could keep on going. So to reiterate, the 1/2, that is the value of my first term. And the notation for that is a sub 1 equals 1/2. So when n equals 1, the value of my first term is 1/2. Okay, so now let's draw a graph of this situation. So I'm going to come down here and draw a graph. I've got n on the horizontal axis, and on the y-axis or the vertical axis, I've got a sub n. So when n is 1, the value of a sub 1 is going to be 1/2. So I'm going to put a dot there on a label of that value, 1/2. And when n is 2, my second term is 1/4. And when n is 3, we've got 1/8. And if we kept on going, these little dots would taper down towards the x-axis, but they're never going to cross it. I'm never going to get 0, and I'm never going to get a negative number, but they're going to snuggle right down to that horizontal axis, right? So this is a decreasing sequence. We are going downhill. And notice that it's a discrete plot. I'm using dots because I don't have any intermediate values. I only know the value at 1, 2, and 3. There's nothing in between. So that's why it's a dot plot. And do these values simmer down as n increases? Yes. So as n goes to infinity, so as we march out here towards infinity, as n increases, those little dots are going down towards 0. Okay, let's take a look at another example. So in this example, I've got a sub n equals -1 to the nth power times 2n plus 1. So let's write out the terms of the sequence. So we're going to write the terms. So again, we could make a little table here for n and a sub n. When n equals 1, I'm going to plug in 1. I'm going to get -1 to the first power. Well, that's not very exciting. And then I get 2 times 1 plus 1, that's just 3. So the answer I'm getting for my first term is just -3. When n is 2, I get -1 squared times, let's see, 2 times 2 is 4, plus 1 is 5. Now, be careful with your negative signs here. -1 squared is a +1, so you actually get 5. And I want to clear up something that a lot of people make a mistake about. You won't do it, because I we talked about it here, but sometimes people get confused between the notation here. So in my first example, -1 squared, that -1 sits out in front. And order of operations tell me just square what's below it. 1 squared is 1, so I get a -1 there. In contrast, when I've got parentheses that are being exponentiated, yeah, I've got -1 times -1, that's going to give me a +1. So just be careful with your signs on these problems. Let's carry on. So if I plug in 3, I'm going to get a -7, etc., etc., etc. So if I write out the terms of my sequence, I'm getting -3, 5, -7, 9. Do you see a pattern? I'm alternating in sign, so this is actually called an alternating sequence. It's not increasing, it's not decreasing. In this case, it's alternating. And it's a bunch of odd numbers. Anyways, if we were to draw the graph, I better make some space for this one. Again, my horizontal axis will be n, and the vertical axis will be a sub n. And when n is 1, I have a -3. So 1, 2, 3, I'm down here. When n is 2, the second term in my sequence has a value of 5. So I'm going to be up here at 5. When n is 3, I'm going to be way down here at -7. When n is 4, I'm going to be up here at 9. And I am just going to keep wiggling around until I run off my paper. So this sequence does not converge. There's no simmering down. It's a pretty wild sequence. It's running away on me. It does not converge. It does not simmer down. So in terms of analyzing sequences, certainly drawing a graph can be a helpful tool. Now, sometimes you have a very complicated formula, and it's better to use limits. I'll show you an example of that. So I suppose I asked you to find the limit as n goes to infinity of n plus 1 over n squared minus 1. Now you might look at this and tell me, oh, I've got infinity over infinity. Well, don't tell me that. You're going to make me very unhappy. The reason is arithmetic with infinity is not defined. So you can't go writing down infinity plus infinity or infinity divided by infinity. Is this infinity? Is it 1? So don't do that. What you do want to do is you want to use some algebra and your limit laws to compute the limit. All right, so that's what we're going to do here. So some tricks that you can do, you can divide by n or maybe divide by n squared. You could try that. Another idea, I see a common factor. So I'm going to pursue that. There's no one right way to go here. But I'm going to factor my denominator and cancel. And so what I end up with is the limit as n goes to infinity of 1 over n minus 1, and that is going to be 0. And again, you could draw a graph of this and verify it visually, but the algebraic root is what you want to be focusing on.